Okay. So, what we're going to do today is go back to what we talked about, the area between curves. The emphasis for me is going to be two things today. Based on what we talked about on the exploration, you could probably, if I bothered to ask you, you could probably tell me what the two things are, but we'll get to them eventually. So today, we're going to find the area between two curves using integration. Top or bottom changes, we didn't, well, we did talk about that in the exploration, so that shouldn't be too bad. We're going to talk about the accumulation process again and focus on the representative rectangle, because as I mentioned on Tuesday, it's integral, no pun intended, into what we're going to do later on. And then you should be able to properly engage in a conversation. Yeah, how strange that is. Okay, so you'll remember we did this, and we found the area between those two curves by doing top minus bottom. We'll get back to that in a second, but I want to make sure that you understand the terminology. Now, this phrase, a region bounded by, shows up a lot. If I look at those two curves, that parabola and that line, there is no bounded region. A bounded region has to have a finite amount of area. There's no finite area there. It just keeps going on and on and on. So then we added the gray area. Where is my gray area? Do you guys see a gray area on your slideshow? Mm-hmm. Where's my gray area?
We didn't get one.
I guess not. Well, that's going to kind of harm the whole thing. Sometimes the bounded region will happen automatically when the two functions intersect. Other times it'll be restricted or bounded by information from the problem. So looking at the gray area there, it's bounded by, what are we doing, 1 to 5? Okay. It's so weird. Am I missing another region? Now I'm missing a pink region. What the hell?
Why did you just include the regions?
I did.
Someone's messing. Is it
It
Adam?
could be Everett. I'd like to blame Everett. He had nothing to do with this. All right. So we talked about f of x being the area. On your slideshow, you'll see that the area is pink. It goes from the curve or the parabola down to the x-axis. And then we talked about g of x, which is below the line, which is green. And then you subtract the green from the pink, and we're left with the gray area, which gives us that body. Okay? And again, we did this already. For those of you that weren't here and you didn't get a chance to look at the exploration, I would suggest you go back and take a look at it. There's the fancy schmancy, what I call calculus speak for explaining that. It doesn't really matter because you understand how that works. But what's important is that little phrase that says f of x is greater than or equal to g of x. One of the things you're going to have to be able to figure out is which function is on top. Sometimes that will be as easy as graphing it on your calculator, graphing it on Desmos. Other times, if for instance it's not a calculator problem, you're going to have to figure out some sneaky way to figure out which one is on top. Okay, we'll talk about that a little bit later. The big thing to come out of this is you're going to need top minus bottom. That is a buzz phrase that we will use over and over and over again. Always top minus bottom. Until it's not. That comes later. Yes, sir?
What if it's under the x-axis?
Ooh, great question. What if it's under the x-axis? There's two answers to your question. One is we don't do those. And number two, you still have an area below the x-axis. It would just be a negative area.
Would it be bottom minus top?
Still becomes top minus bottom, but it becomes minus a negative area. Show on that first time. Okay, you're done. Here we go. Ooh, look, that's how important it is. It changes colors. Oh, pretty.
It's the other one that changes colors.
What's that?
What is your one that changes color?
Yeah, you had the colored graphs. I get the top minus bottom that changes colors. So it's a push, we'll call it. In Vegas, they call that a push. So you know it must be important when it changes colors and it has its own shadow. Ooh. I know. Do you have the shadow? Oh, all right. Well, again, another push. again, for those of you that weren't here on Tuesday, this is a really important idea, and that is this concept of a representative rectangle. So the theory is this: if I can find the area of that light blue rectangle, I can use calculus, in particular integrals, to add up all those rectangles, or accumulate all those rectangles, and when I'm done, I have the area between the two figures. Okay, that's what we're doing. And again, we talked a little bit about why that's relevant. It's going to become important much later on. Again, for those of you that weren't there, you find the height of that rectangle by doing top minus bottom again. Okay, f of w minus g of w. How thick is that rectangle? Andrew, I think you were the one that enlightened us on this. How wide is that rectangle?
Like approaching 0.
Good, and what do we use to represent that?
W.
No. Anybody remember? Nope. dx. Okay, that's where the dx comes in. All right. So, let's do an example. Now, I clicked too much there. I didn't want to do all of that. But here's the setup. The severity of the problem or the difficulty of the problem will dictate how much work you have to do ahead of time. So I picked two nice easy graphs, an x squared and a square root of x. I also already gave you the picture. And in that picture, there's a whole bunch of information. For instance, I now see that there's a bounded region there, that little cat's eye looking region, or that leaf-shaped region. I also showed you, or made it clear, where those regions intersect. Now, suppose you didn't have the graph. How would you find out where the regions intersect?
You can set it equal to each other.
Bingo. Is it safe to assume you could all solve that? Yes? Okay. So you'd get two answers. X would be equal to 0, x would be equal to 1. Also, imagine we didn't know which function was on top. Once I set them equal and solve, I can figure out which one is on top by picking some random number between 0 and 1 and plugging and chugging. Okay, so let's suppose I do 1/2. If I calculate f of 1/2 and g of 1/2, I can get some values here. So this would be 1/4. What's the square root of 1/2?
1 over root 2.
Which is?
Root 2 over 2?
Which is? Approximately? Anybody don't know? You got calculators, right? Tell me what 1 over the square root of 2 is.
Point 7.
Okay. Which one's on top? G of x, correct. Okay. Make sure if you're going to use that method to determine which one is on top, you take a number inside the area that we're going to be talking about. Okay, so in this case from 0 to 1. Realistically speaking, most of the time, however, you're going to pick up your technology and use your technology to come up with that bad boy. Or you're going to rely on somebody to give you a picture. You'll see on the homework, there are some problems on the homework where they give you a picture like this and ask you to find a region. There are other problems where they just give you the two functions. So I want to prepare you for both scenarios. Okay, now, my goal, after I have that representative rectangle, is to come up with the area of that representative rectangle. And some of you might not need this early on. You might just dive right into top minus bottom and solve it that way. That's okay too. But like I mentioned last week, I know where we're going, I know how difficult it's going to be, and this representative rectangle will make your life a lot easier. Okay? So, how tall is that rectangle? Who's talking? Maria, what'd you say?
Root of x minus x squared.
Root of x minus x squared. Top minus bottom. How wide is that rectangle? D of x, or dx, yeah. Same thing. Okay. That's the area of one rectangle. Square root of x minus x squared, all of that times dx. And then, I just have to add all those rectangles together. How do you add those rectangles together? You do an integral. Okay, so there's our rectangle. And then, in order to find the area, you set up an integral from 0 to 1. It also seems trivial at this point in time, but that A equals is very important. Because later on, we're going to be calculating volume. And you need to denote, did I just find an area or did I find a volume? Early on for us, everything today is going to be area, but still, get in the habit of writing A equals. This is a function that you could easily calculate the antiderivative of, plug in 1, plug in 0, or you can FN int the snot out of that one, it doesn't matter. Most of the time you'll find on the homework tonight, the integrals are not difficult. It's the setup that you really want to focus on. Am I suggesting you FN int every problem? No. It is a good practice to grind out these integrals. Okay, questions so far? We're good? All right, the last bit that we did then, I'm sorry, I'm chewing the mint at the same time I'm trying to talk, is what happens when the top and bottom changes. Anytime the top and bottom changes, you need to write another integral because the top is no longer the top and we don't get top minus bottom, we get bottom minus top. That's not good. So, if I have a region like this, you'll notice all of a sudden, when I start at A and I start moving to the right, when I reach that first intersection point, let me start over. If I start at A, then the blue function is on top, the green is on the bottom. When I get to that first intersection point, all of a sudden things flip over. The green is on top, the blue is on the bottom. That requires a new integral. Then I get to the second point of intersection and it flips back. The blue is on top, the green is on the bottom. So when solving that problem, you're going to need 3 different integrals. There we go. Create an integral for each individual region. Which also means that you're going to need to know where those points of intersection are so you know when do the functions switch positions from top to bottom. So let's start this one from scratch. Area bounded by the graph of sine of x and cosine of x from 0 to pi over 2. If you're sketching this, make sure before you dive into the problem that you actually have a bounded region. Is it a finite region? If you're at a point where it goes on and on forever, then you're probably doing something wrong. As the question asks, what information are we missing? Do we know our limits of integration?
Mm-hmm.
What are they?
0 to pi
0 to pi over
over 4. Well, totally a pi over 2. Like
pi over 2, okay? What else do we know or don't we know? Do you know what it looks like? How do you know what it looks like? Did you graph it? Did I give you the picture? I gave you that. I'm an idiot. God, I suck at this job. Region 1, Region 2. The reason I chose this as an example is because the top and the bottom change. Did I give you anything else? Is that it? Okay, good. Solve the problem. Set up your 2 different integrals. Hopefully if you've been listening, you realize there's 2 different integrals. Set up your 2 different integrals. Grind those out. Come up with a final answer. Don't forget your representative rectangles. I did not include those Get in the habit of drawing those. I will require them.
Man, sure. You and I did scold up, right? You weren't sure. Yeah. Okay, just wanna make sure we're on the same page here.
It's longer than it was.
It is, yeah. What are we doing here? From where to where? Sure about that? Because what happens if that's right? So you need two different.
You need an integral to do R1 and you need an integral to do R2.
Regular, perfect. Don't forget your dx. Good.
Why are they the same? So I have to make house like
What do we got, boss?
It's concept, I'm okay with that, yeah. The concept is more important than the actual numerical value. Heather, you got it?
as the first. Oh.
Good, okay, so look at region 1, which one's on top? Good, which one's on the bottom? Good, so do cosine x minus sin x, top minus bottom. Don't forget your dx. You got it?
Oh, how did you do it? Sorry, what you saying?
Oh, no, and then
Oh, how we doing? Yeah? Like a villain?
wait, I think I was kind of confused on like the representative like rectangles, like remember those, like after you draw one. Sorry, I'm
You haven't
not-
asked a question yet, so I'm just, sorry.
Every time, those aren't even in America anymore, right? Did you say?
I'm sorry, what?
They don't sell this one, like this specific like thing in the US. So I got that in the shop.
I was gonna call BS on it, but then I see the bottom and it says, "Deval possible or say David never heard of it, they never never." Sorry, I'll treat it as solve your Denmarkian made in the US.
Sorry, you have to put it.
All right, so what's your question?
So after you draw the big site and six, you're gonna have to put it in use like I did that.
Use the representative rectangle to
You're doing so
help
good.
solve the problem. But again, early on, when you get something like this, which is fairly straightforward, you're gonna be asking yourself, why did I bother with this stupid segment? Because I know what I'm doing. When we get to stuff later on, you're gonna need that representative rectangle and all elements.
Okay, so for right now, all we really need to do is just draw.
See how it dumps it here, so it's more safer.
What do you got?
More safer.
More safer. Like that.
I got two.
You good? Uh-huh.
No.
Okay.
I chose.
Ask you about
You subtract them?
for the when you added it,
All right, problems? We're good? So, what I've got, whoops, I jumped to the next problem. Okay. I don't have it, so I'm gonna have to do it by hand. Chris, you're up, buddy. Color preference.
I was pink.
Pink. I can do, is that okay?
Yeah.
All right. All right, go. Let's go R1 first.
Okay, so the area is
I got you started.
okay, so cosine minus sine of x from 0 to pi over 4.
How do you do? How did you
Well,
do?
you need a dx.
Oh, why do I need the dx there?
Because it's like infinite. It's like approaching 0.
Yeah, two reasons. Number one, it represents the width of our representative rectangle, which I haven't drawn yet, so I'll do that now. Yep. And it also denotes what my variable is in the problem. Okay, which is ridiculous because we only have one variable here. Oh, let's change colors for the second one. Are you good with that? Let's see, erase. I'm not going to. I'm just going to change colors. What do you want? Green, blue?
Sure, green.
Green, blue, light green?
I'll go with light green.
Light green. Good. Probably won't show up very well. Good choice. Oh, no, it does. Okay. Integral from?
Pi over 4 to pi over 2.
Uh-huh.
Cosine, or it's sine x minus cosine x. dx.
Good. Any problems? A couple things to remember when you're setting up integrals. The lower limit of integration has to always be smaller than the upper limit of integration. Good. Now, solving this is up to you. I know a lot of you just FN into it, which is fine because this isn't necessarily about grinding out integrals right now. This is just understanding the concept. Ooh, that green's a little hard to see, but we'll go with it. Okay? Well done. Questions? We're good? Excellent. Chris, answer?
0.828.
Can somebody confirm 0.828?
Do you
Oh,
convert
yeah.
this to decimals? Do you want us to decimals or exact?
It doesn't matter to me. It depends on how you did it. He FN inted, they FN inted. Did you do it by hand? Did anybody do it by hand? What's the fractional value for, or a square rooted radical value of that, if you will?
I think it's root 2 minus 1 times 2, so I just,
Root 2 minus 1 times 2?
yeah.
Okay,
So I just,
sounds good to me. Excellent. Problems? Okay. Did I give you a picture of this one too?
Yes.
I did?
Pick it up.
All right, so there's your picture. For those of you that are having trouble, I'll give you some help. Why can't I get red here? Hold on. That's green. Where's red? Close enough. Red. Green. Blue. So notice we now have a bounded region. That bounded region is formed by the red line, the blue line, and the green cubic. Everything is peachy keen when we start at that first point at -4. Then, when we start here and we start moving to the right, as we accumulate, everything's fine until we get to the y-axis. Once we hit the y-axis, hilarity ensues. Top stays the same, but the bottom changes. So therefore, we end up with two different regions, and like the other problem, we end up with two different integrals. Problems. Okay. So R1 is found doing that. I'm going from -4 to 0, remember the smaller number on the bottom, of the top, which is the red, minus the bottom, which is the blue, and I've got a dx. So again, remember that x plus 6 minus -1/2 x, dx is the area of a representative rectangle, which I have drawn. That'll give you the area of region 1, then region 2 would be what? From what to what? Say again? 0 to 2 of? Big.
You're right, Rob.
Again, I would simplify that first, because x plus 1/2 x is 3/2 x. The bottom one you can't necessarily simplify, you just got to grind it out, get your answers. Whether you f-edit it or you do it by hand is entirely up to you, and you get your answer. Problems? Beautiful. Now, there's two ways to teach this lesson. One way is what I'm doing, which is we're just going to focus on when our representative rectangle is vertical. However, I'm going to show you some examples on Wednesday where that's not so easy to do. And we want to change the representative rectangle to be horizontal. And hence the reason I think it's important that you start grinding these out and get an idea of what you're doing. If this turns out to be not challenging that much, then Wednesday's lesson will be easy peasy. So we're going to stop there. Questions? We're good? Excellent. Let me stop my recording before I start swearing.